regression analysis. This is the topic of biostatistics and research methodology and applied mathematics, biostatistics. Content of this topic includes concept, method of least squares, fitting the lines of regression, equations and application, standard error of regression, multiple regression, and correlation versus regression. Concept of regression analysis. Definition: regression analysis is a statistical technique that defines the functional relationship between two variables by the best fitting straight line. Regression analysis is a mathematical measure of the average relationship between two or more variables in terms of the original units of the data. Simple meaning of regression is stepping back or returning to the average. Line of regression. Two variables' data are plotted on a graph. Their relation is represented by curve. It's called as curve of regression or nonlinear regression between two variables. Two variables' data are plotted on a graph. Their relation is represented by straight line. Is called as linear regression between two variables. Line of regression is the line that gives the best estimate of one variable for any given value of the other variable. The line of regression is located as close as possible to all the points of a scatter chart. In regression analysis, two variables must be defined either as independent variable or dependent variable. The variable which influences the value or used for prediction of other variable is called as independent variable. Independent variable is also recognized as regressor, predictor, or explanatory variable. The variable whose value is influenced or predicted by other variable is called as dependent variable. Dependent variable is also recognized as regressed or explained variable. In XY scatter plot, Y is the dependent variable or response variable, X is the independent variable, A is the Y-intercept, and B is the slope. If the experiments are performed without error, values of X and Y give the plot, results in a 45-degree line, where slope is equal to 1. However, real experiments are not error-free, and a plot of X and Y data rarely exactly fits a straight line. For example, drug potency and assay result, as given in this table. The plot of these data is given here. Now how can we draw a straight line? Draw a straight line that connected to middle points, or draw a straight line that connected to at least 3 points, or draw a straight line that connected to every point. So, which one is best method to draw the straight line? It is a problem to obtain a line to fit data that are not error-free, as the line does not go exactly through all of the points. A good line, however, should come close to the experimental points. The best straight line describing the relationship of X and Y is the line that minimizes the sum of squares of the vertical distances of each point from the fitted line. Mathematical definition of sum of squares is sigma of y minus y e whole square, where y is experimental point and y e is corresponding point or estimated value. The line constructed according to this definition of sum of squares is called least squares line. According to the principle of the least squares, to determine the constant a and b in such a way as the sum of square become minimum, equations are given below. Slope is denoted as b, while a represents intercept. Let's identify slope and intercept of the previous data of drug potency and assay result. To calculate intercept, we need value of x bar and y bar, and further, we need to extend the table to calculate values needed to solve equation of slope. Now, step by step calculate the values of sigma x, sigma y, sigma xy, sigma x square, and sigma y square. Now, identify the value of x bar and y bar. X bar is 90, and y bar found is 88.25. Now calculate slope. The value of slope calculated is 0.915. Now calculate intercept. Intercept found is 5.9. The least squares estimates A and B, that is, intercept and slope respectively. These parameters are used to compute drug potency based on the assay response using equation given below. Question: unknown sample that has an assay value of 90. Then what will be the actual true potency of sample? Use the above equation, place the value of assay, and find out the actual true potency. Potency found is 91.9. Let us recall, meaning of regression. Regression is stepping back, or returning to the average. It is best fitting straight line, average relationship. Another important aspect of regression is mathematical definition of sum of squares, and sum of square become minimum. For the better understanding of regression line, let's take a plot of x and y variable with 6 observation points. Now, draw a straight line. The difference seen of observation point from straight line is due to experiment error. The difference is numerically computed as sum of square. When this difference becomes minimum, that means when we reach to minimum sum of square, then only we get the best fitting straight line. Fitting the lines of regression. Line of regression is the line that gives the best estimate of one variable for any given value of the other variable. Line of regression of y on x is the line which gives the best estimate of the value of y for any specified value of x. for two variables, that is x and y. There is two lines of regression. So, other regression line is line of regression of x on y is the line which gives the best estimate of the value of x for any specified value of y. Let us see first line of regression of y on x, which gives the best estimate of the values of y for any specified value of x. Let us take general example with values of x and y and plot a graph as shown here. In this plot, dot represent the point of observed value for any point, generally represented as xi, yi. Let's draw the best fitting straight line for current condition. This is the line of regression of y on x. Now, for the line of regression of y on x, the estimated point of the observed values are located on line of regression, as shown in this plot. Estimated point generally represented as hi is equal to xi, a plus bxi. For x coordinate, because this is the line of regression of y on x, x is independent variable. Thus, the value of x remains same, whether at observed point or estimated point. For y coordinate, because this is the line of regression of y on x, y is dependent variable. Thus, the value of y is changed. For observed points pi is yi, and for estimated point at line of regression is a plus bxi. Sum of square of error of estimate e is equal to sigma of y minus ye whole square, ultimately, is equal to sigma of yi minus a minus bxi whole square. For line of regression of y on x, the equations of slope and intercept are as given here. Line of regression of x on y, which gives the best estimate of the values of x for any specified value of y. Let us take general example with values of x and y and plot a graph as shown here. In this plot, dot represent the point of observed value for any point, generally represented as xi, yi. Let's draw the best fitting straight line for current condition. This is the line of regression of x on y. Now, for the line of regression of x on y, the estimated point of the observed values are located on line of regression, as shown in this plot. Estimated point generally represented as hi is equal to a plus byi, yi. For y coordinate, because this is the line of regression of x on y, y is independent variable. Thus, the value of y remains same, whether at observed point or estimated point. For x coordinate, because this is the line of regression of x on y, x is dependent variable. Thus, the value of x is changed. For observed points pi is xi, and for estimated point at line of regression is a plus byi. Sum of square of error of estimate e is equal to sigma of x minus xe whole square, ultimately, is equal to sigma of xi minus a minus byi whole square. 4. Line of regression of x on y. The equations of slope and intercept are as given here. Equations applied in regression analysis. Simple mathematical equation used as y is equal to a plus bx, that generally popular in science as y is equal to mx plus c. Coefficient of regression, mean slope. Equation for regression line y on x is by x, and for regression line x on y is bx y. We have various ways to calculate coefficient of regression, either by covariance standard deviation or correlation, as shown in these equations. Equation of intercept for y on x and for x on y. Equation of the line of regression used for the best estimate of one variable for any given value of the other variable is given here. Exercise. In a drug stability study, the following data were obtained. The concentration of drug was measured, with time interval as given in table. Find the equation of the two lines of regression. Find the time to decompose to 90% of label claim. First one is to find the equation of the two lines of regression, that is, line of regression of y on x and line of regression of x on y. For the equation of line of regression, we also need to calculate coefficient of regression by x and bx y. For this given data, let us choose time as x and concentration of drug as y variable. Let's extend the table to calculate the values. Those are needed to solve these equations. First, calculate the mean of x and mean of y. Mean of x found is 12.875, and mean of y found is 2.3925. Now, calculate sigma xy. Sigma xy is 233.07. Next, calculate sigma x square. Sigma x square is 2431. Now, calculate sigma y square. Sigma y square is 45.96. Calculation of coefficient of regression, bx, y. Let's put the values in the equation and identify bx, y. Bxy obtained is minus 82.0737. Now put this value in equation of the line of regression x on y and solve this equation. Multiplication of minus 82.0737 with y is minus 82.0737y, and multiplication of minus 82.0737 with 2.3925 is minus 196.3614. Minus into minus sign. Change to plus. Now, take this minus 12.875 to right-hand side. So, that turns to plus 12.875. 196.3614 plus 12.875 is 209.2364. The equation is now resembles as y is equal to mx plus c, equation of slope-intercept form. Here, in the equation of the line of regression of x on y, minus 82.0737 is the value of slope, and 209.2364 is the value to intercept. Calculation of coefficient of regression, by, x. Let's put the values in the equation and identify by, x. Byx obtained is minus 0.0121. Now put this value in equation of the line of regression y on x and solve this equation. Multiplication of minus 0.0121 with x is minus 0.0121x, and multiplication of minus 0.0121 with 12.875 is minus 0.1558, minus into minus sign, change to plus. Now, take this minus 2.3925 to right-hand side. That turns to plus 2.3925. 0.1558 plus 2.3925 is 2.5483. The equation is now resembles as y is equal to mx plus c, equation of slope-intercept form. Here, in the line of regression equation of y on x, minus 0.0121 is the value of slope, and 2.5483 is the value to intercept. Next question is finding the time to decompose to 90% of label claim, 2.25 milligrams. Here is the finding of the time, that is, x variable in table, from the value of 2.25 milligrams, that is, y variable in table. That means we need to calculate the best estimate of x variable for 2.25 value of the y variable. Thus, to identify x from y, we have to use equation of the line of regression of x on y. Put the value of y in the equation and calculate x value. X value found is 24.57. So, the time to decompose to 90% of label claim is 24.57 months. In simple mathematics, we have used equation of slope-intercept, where we first generate a graph from the data of two variables, and then identify the value of slope and intercept. Then, using y is equal to mx plus c equation, we calculate the value of one variable from other variable. However, there is no idea of two equations of slope-intercept. In regression analysis, we have seen that there is 2 lines of regression for 2 variable dataset, and ultimately, there is 2 equations. When we perform regression analysis in any software, such as Excel, we can directly get equation of line of regression. Here the equation of line of regression obtained, where x-axis is time. So, in Excel, x that is independent variable is time. Excel created equation of line of regression, same as we calculated the equation of line of regression for y on x. Now when we take x as concentration of API in Excel, we will get plot like this. We can directly get equation of line of regression. Here the equation of line of regression obtained, where x-axis is concentration. So, in Excel, x that is independent variable is concentration. Excel created equation of line of regression, same as we calculated the equation of line of regression of x on y. Exercise. Using the data given below, find the equation of the 2 lines of regression. Here data are given as y bar is 30, x bar is 40, standard deviation of x is 5, standard deviation of y is 4, and correlation between x and y is 0.8. As to calculate is equations of line of regression. To calculate line of regression, we need the value of x bar and y bar that is given in this exercise. Thus, only to find is the value of bx, y, and by, x. We have seen various equations to calculate coefficient of regression in slide number 17, and from these, the equation that contains standard deviation and correlation is useful for this exercise. First, calculate the value of bx, y. Bx, y found is 1. Now calculate the value of by, x. Byx found is 0.64. Put the values on the equation of line of regression x on y and solve this. So, the equation of line of regression x on y is x is equal to y plus 10. Now, put the values on the equation of line of regression y on x and solve this. The equation of line of regression y on x is y is equal to 0.64x minus 4.4. Question: if 2 regression coefficients are 0.8 and 0.6, the value of the coefficient of correlation is? The coefficient of correlation is the geometric mean of 2 regression coefficients. So, put values of 2 regression coefficients in this equation and calculate correlation. Coefficient of correlation obtained is 0.6928, so right option is D. Standard error of regression. Synonym is standard error of the estimate. The precision of predictions. Standard error of regression is the measure of scatteredness of the observation on the regression line used to estimate or predict the value of the dependent variable for any given value of the independent variable. Represents the average distance that the observed value falls from the regression line. Standard error of the estimate is square root of sum of squares for error upon number of observations, or square root of unexplained variation upon number of observations. Unexplained variation is the variation in y, which is unexplained by the variable x. It is calculated by following equation. Explained variation is the variation in y, which is explained by the variable x. It is calculated by following equation. Standard error of the estimate of y on x. Equation is SYX, given here. In some references you may see such type of equation. Standard error of the estimate of x on y. Equation is SXY, given here. Standard error of the estimate, also calculated from standard deviation and correlation by following equation. Exercise. In a drug stability study, the following data were obtained. Estimate the standard error of the regression of both x on y and y on x. Equations of standard error of the regression is as follow. In SYX equation, we need to first calculate YE. In 4SXY equation, we need to first calculate XE. Calculation of YE and XE performed using these equations. So, we extend the columns of table for calculation of unexplained variation. Let us first calculate the variation in y, which is unexplained by the variable x, sigma of y minus ye whole square. The value found is 0.001263. Now calculate the variation in x, which is unexplained by the variable y sigma of x, minus xe whole square. The value found is 9.475228. Now, calculate standard error of the estimate of y on x. The value found is 0.0126. Now, calculate standard error of the estimate of x on y. The value found is 1.0883. For better understanding of unexplained variation and standard error of the estimate, let's magnify the line of regression x on y. When you see the observed x value, 36, it is upside to the line, while the observed x value, 18, is downside of the line. Here, 18 value is observed value of x, and point of the red arrow shows the estimated value of x. In regression line, x minus xe actually gives the difference of the observed value and estimated value of x. Here, the observed value of x is 18, and its estimated value is 19.65. The difference is minus 1.65. You can see positive differences of observed values lays on above the regression line. Multiple regression. Multiple regression is a statistical technique that can be used to analyze the relationship between a single dependent variable and several independent variables. Dependent variable is response variable, and independent variable is explanatory variable. Multiple regression is an extension of linear regression. Linear regression is y is equal to a plus bx, while multiple regression equation is y is equal to b0 plus b1 x1 plus b2 x2, and so on, where x1, x2 are independent variables, b0 is the intercept, b1, b2 are coefficients relating the xi to the response. Unlike simple regression analysis, which was represented by a straight line, multiple regression represents planes in multidimensional space, difficult to represent graphically. 4. The plane of regression of x1 on x2, x3. Equation is given as below, where x1 is dependent variable, x2, x3 are independent variables, b1 2.3 is partial regression coefficient of x1 on x2, b1 3.2 is partial regression coefficient of x1 on x3. Equation to calculate b1 2.3 is as follow. That represents the change in value of the variable x1 for a unit change in the value of the variable x2 when the variable x3 is held constant. Equation to calculate b1 3.2 is as follow. That represents the change in value of the variable x1 for a unit change in the value of the variable x3 when the variable x2 is held constant. Line of regression of x1 on x2 and x3 is given by x1 minus x1 bar is equal to b1 2.3 into x2 minus x2 bar plus b1 3.2 into x3 minus x3 bar. Exercise. x1, x2, and x3 are excess of heights of father, mother, and son respectively. Of 100 samples with regression, R12 is 0.3, R23 is 0.4, and R31 is 0.5. And standard deviations, sigma 1 is 3, sigma 2 is 2, and sigma 3 is 4. First, to obtain regression equation of x1 on x2 and x3. Second is to estimate the excess of height of father when excess of height of mother and son are 0.7 centimeters and 2.1 centimeters respectively. Here is the regression equation of x1 on x2 and x3. First, we need to calculate b1 2.3 and b1 3.2. b1 2.3 found is 0.1786. Now calculate b1 3.2. b1 3.2 found is 0.3393. So, the regression equation of x1 on x2 and x3 is as given below. Now for question 2. For the value of x2, 0.7, and x3, 2.1 centimeters, identify x1. So place these x2 and x3 values in above equation and identify x1. The value of x1 found is 0.84. Result: excess height of father is 0.84 centimeters, when excess of height of mother and son are 0.7 centimeters and 2.1 centimeters respectively. For 3 variables, the following results are obtained. Find regression line of x1 on x2 and x3. Here is the equation to find the regression line equation. To solve this equation, first we need to calculate b1 2.3. b1 2.3 found is 0.3571. Now calculate b1 3.2. b1 3.2 found is 0.1851. Now, put the values in the equation and try to solve it. The equation of regression line of x1 on x2 and x3 is found as x1 is equal to 0.3571 x2 plus 0.1851 x3 plus 20.147. Correlation versus regression. Let's see differences between correlation and regression. Difference based on definition. Correlation is a statistical tool which studies the relationship between two variables, while regression analysis is a statistical technique that defines the functional relationship between two variables by the best fitting straight line. Variations available in correlation as positive and negative correlation, linear and nonlinear correlation, while in regression analysis is line of regression of y on x and line of regression of x on y. Correlation is a measure of the linear relationship between two variables, which is mutual and symmetric. That is, our xy is equal to our yx, while regression analysis is not symmetric. That is, bxy is not equal to byx. Regression analysis gives the functional relationship between two variables to predict or estimate the value of one variable from another. Correlation. No need to define variables, while regression analysis consider as dependent variable and independent variable. Correlation coefficient or xy is a relative measure of the linear relationship between x and y. Our x-y values lies between -1 to +1, while, in regression analysis, coefficient bxy and byx are absolute measures, representing the change in value of dependent variable for a unit change in the value of the independent variable. Correlation need not imply cause and effect relationship between variables, while in regression analysis clearly indicates the cause and effect relationship, where cause is independent variable and effect is dependent variable. Correlation has a type, nonsense correlation, that is, no logic of relation between variables, while in regression has no such thing like nonsense regression. Correlation analysis confined only to study of linear relationship, thus has limited applications, while regression analysis has much wider applications, as it studies linear as well as nonlinear relationship between variables. End of the topic of regression analysis. You can refer to these mentioned books for this topic. Fundamentals of Statistics by S. E. Gupta. Pharmaceutical Statistics, Practical and Clinical Applications by Sanford Bolton. Please take a note on important study questions. Thank you.